Yesterday I talked about the science of climate change. I talked about um, emission scenarios. Today we're going to talk about greenhouse gas emission reduction. So I'm going to start talking about technical options. Then after the break I'm going to talk about the costs of emission reduction. And then this afternoon we're going to talk about policy instruments for emission reduction. Right? So that's the plan. How can we reduce emissions? Yesterday I talked about where emissions come from, and I introduced the chi identity that is reproduced here. That says that emissions is equal to population, the number of people times per capita income times the energy intensity of the economy times the carbon intensity of the energy system. If that is true, and it's very hard to disagree with that, then the second equation must be true as well. So what do? We take the log on both sides of the equation, so the product becomes the sum, and then we take the first partial derivative in time on both sides of the equation, and then what we have is the proportional growth rate. And dln x dt is just another way of writing the change in x over x, so that is the growth rate. So what does this tell us? If we want to change the growth rate of emissions, dln E dt, then we can do essentially four things. We can reduce the number of people. It's not a policy that would be advisable if you want to get re-elected, but of course it's a very active policy in Zimbabwe, in the Sudan, and also China in subsequent climate negotiations has claimed consistently that its one-child policy is its major contribution to international climate policy. This is of course complete nonsense. The one-child policy was introduced long before climate change was a concern. It was introduced for different reasons than climate change, but nevertheless they have made this claim. Not something that you would want to say if you're a politician in the Netherlands or elsewhere in Europe and you want to get re-elected. That's not something you would advocate. Because we think that it should be left to individuals and households to make those decisions. The second option in this equation is to reduce economic growth. It's a very effective policy. You're looking at here in blue is GDP in the former Soviet Union, and in red you're looking at carbon dioxide emissions from the same places. And what you see is that, if the economy dives, as it did after the wall came down, emissions tend to come down as well. The scale of the economy is much, much smaller. This has been repeated in a number of places all over the world. If the economy collapses for whatever reason, then emissions tend to come down with it. And also the lack of growth in CO2 emissions from Europe over the last 10 years or so is by and large explained by the lack of economic growth. So it's a very effective policy, but again, if you want to get re-elected, then perhaps you should not say we're going to sacrifice economic growth. We're going to create an economic crisis so as to reduce greenhouse gas emissions. That would not be a message that would go down well with probably 99% of the electorate. So that means that you're left with two options only. If you want your emissions to go down, then what you need to do is save a lot of energy or use different sources of energy. And you would need to do so at a rate that overcomes population growth and income growth. That is what you need to do. So yesterday I showed this graph where we looked at global CO2 emissions. And what we found is that yes, particularly energy efficiency improvements have slowed down the growth of emissions. If it hadn't been for energy efficiency improvements, emissions would have been much, much higher, but they're nowhere near as large as income growth. We found the population growing by about 2%, income growing by about 2%. And that means that if you want your emissions to stay stable, your energy intensity and your carbon intensity have to fall together by 4% as well. And then you just keep your emissions stable. You're not reducing them, right? So that gives you an idea of the scale of the task. So let's talk a little bit more about these two basic options. And then I'll throw in some more exotic options towards the end of the lecture. So, first option is to save energy, to get the same level of services, comfort, heat, propulsion, but using less energy. Just alluded to this graph. This is the historic energy saving, about 30% over a 40-year period. So let's make it 0.75% per year. It's not enough to overcome economic growth. It's not enough to overcome population growth. What we need to do if we want to cut emissions is not come up with smarter ways to use energy. That's not enough. What we need to do, because the market has been always doing that, that's why that's about to do this, because energy is a cost. If you're a producer and you make something and the thing that you make delivers the same services, the same goods, the same whatever as the product that your competitor offers, but yours uses less energy, then your customers will want to buy your product rather than the product of your competitor. Because energy is a cost. Right? And if the performance is the same, but the cost is less, then you have a competitive advantage. So market forces have been pushing energy efficiency ever upwards, energy intensity ever downwards. We show it here for the last 40 years. There's been reconstructions of this for the last 100 years, for the last 500 years, and even in one paper for the last 3,000 years. And as far as we know, this has always been going on. And this is roughly a constant that energy efficiency has always been improving, somewhere between 1 or half and 1% per year. And what we need to do is not improve energy efficiency, but accelerate the trend of energy efficiency improvement, which is a different proposition altogether. So we compare single products over time, then what we find is that new models tend to be more energy efficient. But it's not necessarily the case that this energy efficiency is used to save energy. And a good example of that is found in the automotive industry in the United States. In the top graph, you're looking at the fuel efficiency of the average car sold in the US over time. And fuel efficiency is here measured in miles per gallon. We are in the US, so we use this slightly strange unit. But what you see is that between 1980, say, and 2010, this was flat. For every liter of gasoline that you poured into your car, you could get the same kilometers driven out. So you may say this sort of contradicts what you just said, that energy efficiency is always improving. No, it doesn't contradict it at all. In the bottom, you see for the same time period what happened to the cars themselves in the US. One thing you probably are aware of, that American cars have gotten bigger and bigger and bigger and bigger. You just travel across the pond and you're just amazed by the size of the cars at the road. Or at least I am amazed by the sheer size of American cars compared to what you see in Europe. And if you have a bigger car, it also tends to be heavier and you have to do more cooling it along. And that is what you see in the middle graph. The weight of the average car in the US has gone up spectacularly over the same period. And similarly, the horsepower, how fast an engine can pull things and how much an engine can pull, has also been going up quite remarkably. Actually, these three graphs combined are a remarkable feat of engineering. You have cars that are a lot heavier now than they used to be 30 years ago. You have engines with a lot more horsepower than they used to have 30 years ago, and still they use the same amount of fuel per kilometer traveled. That's a remarkable technological progress. But the American customer did not want a more fuel efficient car. They wanted a bigger car and a faster car and a more powerful car. Right? So it's not necessarily the case that technological improvement means saving energy. Now, what do we need to do to accelerate this trend? And that is what it is about. We need to put more engineers on. It's not just that we can say, well, we want faster energy efficiency improvements, right? How does fuel efficiency improve in an engine? By having teams of engineers tinkering with those engines to make them better. This is a difficult thing to do because these engines have been around for about 120 years. So all the obvious improvements have been tried. And by now you really, really need to understand engines to make the contribution to it. So this is work of very specialized engineers, very clever people trying to improve this and actually succeeding, right? Still succeeding despite the 120-year history of the engine. So if you want to accelerate the trend, what you need to do is get cleverer engineers or more engineers, but where would you find them? More engineers does not necessarily help. Where would you get them? The people who have the skills and the interest of tinkering with engines are already doing that. And taking a bunch of economists and say, now, stop studying the economy, now you're going to improve engines. It's not really going to help, right? You just get in the way, probably. And also, if you get those really smart people that can do anything, and there are still, those people are still around, if you take them and you put them on improving fuel efficiency in engines, that means that they're no longer improving computers, or they're no longer inventing new medicine. So that comes at a real cost. Yeah.
Isn't it with the rebound effect that when you improve cars and the price drops, then use it more, and so that it's actually not
there is the rebound effect as well. So for those of you who are not familiar with this, if you improve energy efficiency, then the real price of energy falls. And that means the demand for energy increases. That would further dampen the effect of energy saving. Estimates of the rebound effect are hard to come by. There's plenty of them, but they're not always equally reliable. Most people would argue that the rebound effect is 10 or 20% of the initial saving. There are estimates that put it out up to 120%. There are also estimates that show that it's zero. But yeah, 10-20% is probably a reasonable guess. So that is technological improvement. There's also behavioral change. A lot of energy is wasted. Engineers reckon that about 30% of the energy that we use serves no useful purpose. It does not follow then that you can cut energy use by 30% without incurring the cost. That does not follow. So how do we waste energy? A lot of people, when they're making a cup of tea or a cup of coffee or whatever, boil too much water in the kettle than they really need. So you need 1 cup of tea, and you boil water enough for 5, and then you let the other 4 cups of water cool down again. And the next time you want a cup of tea, you again heat all of that up. That's a sheer waste of energy. No useful purpose whatsoever. And how do you change it? And does that come at no cost? Most of you probably live with other students, right? Some of you may live with an energy Nazi who goes around the house telling you to boil less water, to turn up the light if you leave the bathroom. Those things come at a cost, right? They actually do not necessarily change your behavior because you may not really like this person anymore and you just do it out of spite. Or it may just block in your mind this constant haggling. Or as soon as that person is no longer with you, you just ignore whatever they were saying. Habits are very hard to change. And changing habits is actually comes at a cost, right? The example I just gave you is personal relationships. There's been a lot of experience with the government trying to make us aware of our wasteful energy use, how we really should help save the planet and so on and so forth. Those campaigns do not necessarily bear much fruit. Not terribly expensive, so it's not a lot of money wasted, but the effectiveness tends to be roughly zero. So habits are just very, very difficult. There's also more structural problems. And economists often highlight the principal agent problem. So if you, after dark, you walk around this campus, what you would find is that a lot of lecture halls, lecture rooms have the lights still on, even though there's nobody there. That's the sheer waste of energy. Those lights serve no useful purpose, but they do take up electricity and they do emit carbon dioxide. But how do you solve that? So I am in control of the lighting of this room. As a lecturer, it's my job to make sure that everything is turned on as the lecture ends. If I do so, then money, energy is saved, money is saved, but the reduction in the energy bill of the university goes to the big pot of the university. It doesn't go to me. So I am the agent here. I control the resource, but I do not pay the bills. There's no personal benefit for me whatsoever to turn off the lights. So why would I? This is the smallest problem. The same happens between landlords and people who rent apartments. The landlord is responsible for the insulation, for the heating system, and so on and so forth, for the glazing in your house. But you are the one who's paying the energy bills. So it is in your interest to put double glazing in your house. But you can't because the contract says you're simply not allowed to make structural changes like that to the apartment that you rent. Whereas the landlord has no interest in doing so because these energy savings are not passed through in higher rents. A classical principal agent problem. The way to solve this is to completely rearrange the way the rental market works. The way to solve the lighting problem in this room is that if I come in, flash a card or pin in a code, I am here now, I would have to have my personal electricity account with the university. And if I save electricity, then I get more research money or more travel money or a higher salary. So you would need to change completely the way the university is administered and perhaps also the way labor contracts work. It's feasible. The question is it worth it? The question is, do the labor unions agree and so on and so forth. These things are just difficult to change. Not to say that it's impossible, but it is to say that 30% or so of energy that serves no useful purpose does not imply that just overnight we can cut energy use by 30% without incurring a serious cost, particularly in rearranging the way we live our lives. The third way of saving energy, the first way is technological change, the second is behavioral change, the third way is to simply reduce the demand for electricity. So instead of taking a holiday in Thailand, you should go to the south of England instead. It's very lovely. It comes recommended. Instead of turning up the heat in your house, you should wear an extra sweater. That would also save energy. It's even harder to convince people of these sort of changes. Right? Because now you're really affecting the way we live our lives, the way we use energy. Okay, that was the first serious option, saving energy. Not impossible, but it's nowhere, it's not necessarily easy. The second option is to switch to other types of energy. As I said yesterday, not all fossil fuels are created equal. Particularly the solids are much more carbon intensive than the gaseous fuels. This can really make a difference. What you're looking at here is over a period of 10 years or so in the US, the CO2, and that's given in black, that comes out of the power generation sector in the United States. And what you see is that there's been a substantial emission reduction from about 20 to 50 in the year 2001 to about 2000 in the year 2012. So that's a 10% or so emission reduction. All that comes from the switch from coal to gas. At the very top, you're looking at renewables, basically constant, and in blue, you're looking at hydro, basically constant. In yellow, you're looking at nuclear, basically constant. And then if you compare the top of the red curve across time, then you see that gas and oil and coal have been roughly constant. Oil is phased out. Oil is the silly thing to make electricity from. But what you see is that the brown has come down, coal has come down, coal and gas together have stayed the same roughly, and so gas has taken over from coal, and that's because It's about 2/3. You switch from coal to gas, you cut your emissions by about 1/3 on a per kilowatt basis. And that is what you see happening here. That simply the switch away from coal towards gas has cut a lot of emissions. This has nothing to do with climate policy. You may be aware the US did not have an active climate policy through this period. It has everything to do with the discovery of shale gas. It led to a significant drop in gas prices in the US. Actually, also a significant drop in coal prices in the US and in the rest of the world, but nowhere compared to the drop in gas prices. And these companies have been switching en masse to gas. A lot of the coal actually has ended up in Europe. So in Europe, you see the opposite pattern. They switched away from coal, from gas towards coal because it is so cheap. And also because the Germans got a bit nervous about nuclear. And in Europe, you actually see the opposite. So just changing the composition of your fossil fuel mix can actually help a lot, and can actually help a lot in the short run. Right? This is a 10-year period, which is very quick. You can, of course, go a step further and move away from fossil fuels towards renewables or towards fuels that are carbon free. The two oldest and best proven technologies are nuclear and hydro. The problem there is not the technology. We know how to build nuclear power plants. 400 of them in operation. Same is true for hydro. Lots of them around, and have been around for a long time. We know how to build them. People disagree about the economics of it all. The nuclear in particular, but hydro also to a certain extent, are typically built by companies that are very close to the government or in direct control of the government, and that means their accounts are always a bit murky. It's a bit unclear how much subsidies are really flowing to them, and whether the costs they incur are really costs for the energy, or whether they're doing somebody some political favors. So the economics of these things are actually very, very murky. It's interesting to properly understand what is going on in these companies. But the main issues in nuclear and hydro are simply political acceptance, social acceptance. Definitely in Western Europe, we seem to be moving away from nuclear rather than towards nuclear. Large-scale hydro means filling up mountain valleys with water, and you immediately get a lot of locals protesting that their houses are flooded, or environmentalists protesting that their favorite birds are getting flooded, or their favorite plants. So this is just hard to do. In the US, nuclear is also essentially off the table because they introduced this rule that you have to be liable if something goes wrong and no insurance company wants to touch it. Building a power plant that is uninsured is not wise, and it's very difficult to finance. Nobody just wants to lend you money. Now, I'll give you money to do so. So nuclear and hydro are technical options, but they're just politically and physically, politically and socially not very popular. There's another problem with nuclear, and that's proliferation. If you can build a nuclear power station, you can also build a nuclear bomb, definitely a dirty bomb. You want to make a serious dent in greenhouse gas emissions, then we should have nuclear power plants everywhere, not just in nice countries like Finland, or in not so nice but well organized countries like Iran. You should also need to have nuclear power plants in Syria, in the Central African Republic. And then you get sort of into risks of, do you really trust these guys to run that piece of technology that is so very complicated, and if you do something wrong with it, it gets very, very dangerous. And if you steal the fuel, you can really, really hurt people. Probably not. And also for that reason, nuclear is less of an option for greenhouse gas emission reduction than some people would like us to believe. So that leaves us the more unconventional renewables, wind, solar, biomass. Just tidal as well. There's no physical problem here. If we just look at the amount of energy that is in the wind, in the waves, in the sun, we can supply the world's energy needs 10 times over. Physical resources, no problem. There's also no technical problem. We know how to convert solar light into electricity. We know how to harness wind to make electricity. So there's no technical problem either. We know how to do these conversions. The problem is again economic, social, political. So wind at the moment is still fairly expensive. Coal-fired electricity costs about 4 cents per kilowatt hour. Gas-fired costs about 6 cents per kilowatt hour. Wind is still around 8 cents per kilowatt hour. So if it were possible to switch completely away from coal towards wind, then you would double the cost of electricity. You can't do that because wind is unpredictable and intermittent. So you can't count on the wind being there when you need it. So you always need backup plants in case of a sudden drop in wind. So that makes wind more expensive. There's also in Europe increasing protests against the expansion of wind farms. They're visually intrusive because they hurt birds and bats, and we have now so many of them that occasionally one falls down. Fortunately, no turbine has ever actually ever killed somebody, but it's just a matter of time, right? Because we tend to put these things in new places. That is nice hills, and people like to go walk their dog and that sort of thing. And if a wind turbine comes crashing down on top of you, then that would not be good. And that is just a matter of time before this happens, right? Solar is a bit more reliable in the sense that it has more momentum in the system, but it's more expensive still. So wind is around 8 cents per kilowatt hour. Solar, we're still talking about 10 to 12 cents per kilowatt hour. The crucial difference between wind and solar is that for wind, technological progress has stopped about 10 years ago. 10 years ago, it was 8 cents per kilowatt hour, still 8 cents per kilowatt hour. There's still a lot of technological progress in solar. 10 years ago, it wasn't 10 or 12, but it was more like 20 to 25 cents per kilowatt hour. So there's very rapid technological progress, mostly coming from spillovers in material science. Whereas wind is an old technology, mechanical engineering, top aeroplanes, essentially. Solar is sort of like new science and exciting science, and there's a lot of investment in these things. And you can expect further progress in solar. It's not there yet, but it's getting there. Wind and solar both have the problem that they tend to be more concentrated where there's fewer people. So you have the problem of transport of electricity as well, which is either very costly or you lose a lot of electricity on the way, which is also very costly. And simply shipping electricity from, say, the west coast of Ireland, where there's a lot of wind, to London, where there's a lot of demand for electricity would set you back to 0.4 cents per kilowatt hour. So that would add 50% or so to the cost. Wind and solar are good for making electricity. If you're driving a car or flying an aeroplane, that is not much use. The best option we have for making liquid fuels is biomass. The current generation, the first generation of biofuels are simply not up to the task. There's a couple of problems with that. The first is that it's very expensive compared to fossil fuels. The reason for that is simple. Coal and oil are carbohydrates. They're plant material that have been, in the case of coal, nicely compacted by Mother Nature over a period of millions of years. Crude oil is roughly the same, right? It's been sort of like nicely converted for you through geological processes. Biomass is recent plant material, still plant material, but you have to do all the harvesting, all the compacting, all the drying, all the converting yourself. Whereas with coal, plants have been nicely compacted for you. If you take a field of maize stalks, you need to get a tractor in, compact them, dry them, and so on and so forth. You have to do all that work yourself without adding to the energy content of the fuel. Right? There's a lot of processing involved. So for that reason, biomass simply can't compete. Biomass does compete with food. The stuff that we're currently burning for energy is stuff humans can eat or stuff animals can eat that we then eat. So the shift away from growing crops for food to crops for energy at the moment drives up food prices around the world. And particularly the US is doing this at a fairly massive scale. These things can also be bad for the environment. So Brazilian ethanol comes from Brazilian sugarcane. Sugarcane is not grown in the rainforest, but sugarcane pushes soy away from where it used to grow. The soy pushes away the grassland where it used to be, and the grassland pushes into the rainforest. So it's not that we grow sugarcane in where 10 years ago it was rainforest, but because of the chain of events, we do cut down rainforests to make ethanol. Biomass, because it is necessarily more impure than old biomass, old fossil fuels, also creates health problems. In Germany, it used to be the case that you could smell poor neighborhoods because they were burning poor fuels. Nowadays, you can smell the rich neighborhoods in Germany because they all have biomass burners in their house. They're not properly maintained, run by a bunch of amateurs, and they're burning fuels that really are not fit for burning. And the result is a lot of incomplete combustion. That is what you smell. If you smell a fire, if you smell a car, that's because the fuels are not properly burned. Now, it's not the smell that you should be worried about, but the things that you smell are actually your nose warning you there's a lot of carcinogenic material here. Get out. Right? So there's health issues as well. The basic problem with using crops for fuel rather than for food is that this is primitive. The agricultural revolution started about 10,000 years ago, and over those 10,000 years, we have completely changed the plants that we use for eating. The grains that we eat, the fruits that we eat, they have very little resemblance to their wild ancestors. and we put a lot of effort into selective breeding. We haven't done that for crops for energy at all. We've made no effort whatsoever of making these things better for energy. So we're essentially with crops for fuel, we're 10,000 years behind crops for energy. It suggests that there's a lot of prospect for technological progress. And of course, nowadays we're a lot smarter than the people 10,000 years ago, or at least we know a lot more about selective breeding, and we now have genetic engineering at our disposal. So you can expect in the not too distant future, 10 years, 20 years, 30 years, a lot of technological progress in growing crops for fuel. There's been some spectacular developments in the lab. I want to raise one. They've genetically engineered algae so that you put them in a vat of water, nice warm water, and then 2 days later there's a film of diesel floating on. We now have algae that can make diesel just from sunlight and a bit of food. Not been able to scale this up from the lab to the factory. Not been able to sell this commercially, but those things are just a matter of time. Right? The life sciences are getting really, really interested in this sort of thing. And if indeed you can somehow magic up something that is very similar to diesel, there's a potential very rich rewards. Right? If you're the first to master that at a commercial scale, you will be very, very rich. Not now, not today, but in 20 years' time, there may be a lot possible. Not going to step away from the Chi identity and talk a little bit about 3 other options to reduce greenhouse gas emissions. So yesterday I mentioned that deforestation, replacing tall trees with small grass, is a source of emissions. So if you can reverse that process, you have negative emissions. You're sucking carbon out of the atmosphere. That's how plants grow. Through photosynthesis, right? In North America and Europe, the forests are of course growing back already. Right? We cut them down a long time ago. You don't need all that agricultural land anymore. So here, forests are growing back, sucking up carbon. Not so in the tropics. So if you could convince the people in the Congo, the people in Indonesia, the people in Brazil to stop cutting down forests or actually burning them, because they mostly do, then that would save avoid a lot of emissions. Very good reasons for doing so, other than climate policy, particularly in nature conservation, biodiversity policies. And because of that reason, people have been trying for a number of decades now to do this, but without much success. This is an attractive option in the sense of the scale of its contribution to the problem, but it's not an easy option. If we knew how to do this, we would have done so a long, long time ago. And some countries are sort of like seeing success in this, or at least so they claim. Some of it may have to do with policy, some of it may have to do with completely other trends. An option outside of the Chi identity completely is carbon capture and storage. Essentially what you do there is you take your smokestack and the flue gas that comes out of the smokestack, the exhaust gas, and you separate out the carbon dioxide and you stick it somewhere safe. either deep on the ground or deep underwater. You know how to do this. You have bottled water with you. Most of you would have drank at least one beer in your life. The bubbles in your water, the bubbles in your Coke, the bubbles in your beer are CO2. So that must mean that we know how to get CO2 out of composition of gases, right? That's a proven technology. We obviously also know how to stick CO2 somewhere. Travel across the Netherlands and you visit the greenhouses that are here, you would find that a lot of them have enhanced CO2 concentrations because that makes plants grow faster. And in a lot of oil fields, particularly older oil fields, people are injecting CO2 because that increases the pressure in the oil field and makes the oil come out faster. You know how to do it. But again, the problem is economics and politics. A CO2 separation plant is not cheap. It adds about 25% to the capital cost of a new built power plant. 25%. And it also takes a lot of energy. And it sucks up about 30% of the electricity that is generated in that power plant to separate out the CO2. So your capital costs go up by 25% and your output goes down by 30%. So this is not cheap, right? And that is if you do it in a new build power plant. If you do it in an existing power plant that you need to retrofit, it's a lot more expensive still because you need to rewire all your pipes. Right? So this is not cheap. There is an issue with scale. CO2 is much less dense than oil and gas. So people at MIT have done some calculations. If you want to make a serious dent in CO2 emissions across the world through carbon capture and storage, the amount of pipes that we would need is 5 times the amount of pipes that we currently have to transport oil and gas. A lot of steel, that's a lot of concrete, that's a lot of money. Right? So this is not a cheap or easy option. And then the issue is, of course, what do you do with the CO2? Maybe you stick it. You can stick it into the ocean, but you have to go 700-800 meters deep to apply the pressure high enough to keep it there, or you can stick it in geological reservoirs. And the question is, how leaky are they? For sticking CO2 in the ground now and having it all leak out within 10 years is not good, right? You want to stick it in permanently. And there's safety issues as well. CO2 is denser than air. So if you have a leak of CO2, a massive release of CO2, then that will push out the oxygen. It takes about 15 minutes or so for the wind to blow away the CO2, but 15 minutes without oxygen is not good for you. And there's indeed been an incident where a Nigerian village, through geological reasons, not because of carbon storage, had the earth essentially burp CO2 and everybody's dead, right? So if we create more of these CO2 stores underground in places that are not safe, but in places that are visited by humans, then we have an issue, right? So there's problems there. And of course, carbon capture and storage is your ultimate end-of-life technology. It is instead of solving the structural problem, you just take away the problem and stick it somewhere safe at a cost, necessarily at a cost. And that means that if you solve the climate problem through this, then the climate problem is gone, you're still incurring the cost. Problem is gone, politicians lose interest. the problem is done, but you're still imposing a carbon tax to pay for the carbon capture and storage. How long before a politician say, why are we paying for a problem that is not there anymore? And because this is necessarily a cost to the power generators, because you do divert 30% of your energy into capturing CO2, as soon as the political incentive to do something about the problem is gone, if the problem is gone, the political incentive will disappear, then all the CO2 just gets planted back into the atmosphere a day after. So that is not very handy. The final set of options that we have is, and I'll be quick, is to change the climate back. The problem with climate change is that we put stuff in the atmosphere that warms the planet, so let's put stuff in the atmosphere that cools the planet. One option is to put a lot of sulfur in the atmosphere. If you pick the right sort of sulfur, we're not causing acid rain. We know that natural dust in the atmosphere cools the planet down. We know that a lot of oceanic dust in the atmosphere cools the planet down. So why not put in some artificial dust on top? The scale of this project is astonishingly small. Sulfur is a waste product. There's piles of sulfur lying around the power plant, so you can get it for free. And if you have a fleet of 4 Boeing 747s, you can put enough dust in the atmosphere to cool the planet down by 2, 3, 4 degrees. So that's the cost of a small airliner. Right? Straight away. A country like Luxembourg could afford to do this. Probably a country like the Maldives could afford to do this on their own. Right? So that is an option. The other option is to put mirrors in space. All the energy from the sun that reaches the planet goes through actually a very small area. You can sort of like draw a line from the top of the sun to the bottom of the earth, and then from the top of the sun to the top of the earth, and then from the bottom of the sun to the top and the bottom of the earth. You would find that there's a very small area in between where all the energy that reaches us has to go through. Which means that if you put mirrors in that spot, the best spot is L1, where sort of you don't have to maneuver because the gravity pulls those mirrors, gravity of the sun and the earth pulls those mirrors equally in both directions, so they just stay put nicely. If you put mirrors in L1, then you can reflect a lot of solar light. Obviously, you don't want to put mirrors in that are there always like this, but you want to put movable mirrors in. Sometimes are like this, reflect all the sunlight, and sometimes all the sunlight go through, right? Depending on your desires. You don't need a whole lot of them. The area there is only 10 square kilometers or so. You only need to reflect a little bit of the sunlight. Then you cool down the planet again. There's two big problems with these sort of interventions. The first is the great uncertainty. I hope to have impressed on you yesterday that our understanding of the climate system is very, very limited. That we don't understand the climate system nearly well enough to predict the effects of our first intervention, putting CO2 in the atmosphere. What we're proposing here is to have two interventions and make sure that the two cancel each other out. Which some climatologists have described as science fiction. We simply do not know enough of it. Of course, cancelling out the increase in the global mean surface air temperature does not mean that you necessarily also cancel out the pattern of temperature changes or the pattern of rainfall changes. So you also need to be very careful. What are we cancelling out? Even if you could predict it with some uncertainty. People have tried in the past Some of these experiments, mostly weather modification, went quite wrong. The Greek colonels liked a bit of rainfall, seeded clouds, and as a result, it flooded a lot in Turkey. They sort of like fell, but in the wrong place. The Soviets diverted a lot of rivers from going to the Arctic that are not much used to their cotton fields. Didn't really help them, but it is, people suspect, one of the causes of the Great Famine in China in the 60s. So we don't quite understand these things. The other big problem with this is the geopolitics of it all. So those mirrors in space, and whether they're in this position or this position, require that there's somebody on Earth flicking the switch. Now, who would that somebody be? In the near future, well, we actually don't know. At the moment, it would be Barack Obama, but we don't know who will succeed him come November, right? And maybe somebody we like, but maybe somebody we don't like. In the recent past, there have been American presidents that were less than popular outside of the US, right? In 10 years' time, maybe the Chinese will be capable of doing it. And do we trust them to control our climate? Similarly, for putting dust in the atmosphere. As I said, this can be done by a small airliner. And I gave you the example of Luxembourg and the Maldives. North Korea can do this too. ISIS can probably do it as well. Right? These are dangerous technologies. Because they are dangerous, we better understand them. We better understand what we can do against them. If North Korea goes up to 4 Boeing 747s, you can shoot them down. But you can also inject dust into the atmosphere by cannon, and then it's much harder to stop them. So we better understand this, and maybe all goes wrong in climate change, and then we better have this option available that at least we can try to change the climate back. But there's a serious option for mainstream climate policy, perhaps not now.